Good morning. So today we are going to discuss the scale effects problem of the first generation Schumpeterian models, and then we also look at what are the proposed solutions. Let me share my slides first. I have a couple of slides for this lecture. So my discussion basically centers on around this paper. So the scale effects problem is best, I think, explained in this paper by Lenz and Pareto, published in Journal of Economic Growth. So let's try to understand what the scale effect is. So in the first generation Schumpeterian models, and when I say first generation, what I mean is Romer 1990, Grossman and Helpman 1991, and Aghion and Howitt 1992. So in these papers, a larger workforce allocated to R&D, or more typically a larger workforce in the final goods sector, implies a larger growth rate, larger long-run growth rate. Okay, so the important thing is that it is the long-run growth rate. Okay, long-run growth rate of GDP per capita. So that's a theoretical prediction of all of these first-generation models. And Charles Jones, in a paper published in 1995, he showed that this is not true in reality. Okay, in reality, R&D workforce and population actually increases, but long-run growth rate of the U.S. economy and some other, developed economies, that long-run growth rate is roughly constant. It's around 2% per year. Okay, so let me show you this figure from the Jones paper. You see it, right? The figure right now. Guys, do you see the figure right now? Can you please respond?
Yes.
Yes.
All right. Okay, great. So in this figure, what you see is the actual evolution of GDP per capita. So the solid line that fluctuates is GDP per capita in the United States from 1880 to 1980. So in a 100-year sample, we observe this fluctuation, but the trend line, which basically gives you the long-run growth rate, right? So the slope of the trend line basically gives you the long-run growth rate, and we see that it is roughly constant. So there, of course, if you change the sample, you observe different growth rates, but it is to a large extent a constant growth rate. Okay, so in fact, if you look at this figure, you can understand the constancy of it, right? But in the meantime, if you look at the evolution of R&D workforce, let me find that figure right here. So if you look at the evolution of R&D workforce in several developed countries, you observe the growth rate of L, right? So L is increasing fastly after the Second World War. So that's the problem. Okay, that's the problem we want to understand. So in the models we studied last week, where do we find the scale effect? Well, it is that partial derivative being positive, right? We studied two models, Romer 1990 and Aghion and Howitt 1992. Of course, we just studied them, in a very simple way, the textbook versions. But in both of these versions, we find that long-run growth rate positively increases with the, positively changes with the workforce employed in the final goods sector. If that workforce is larger, profitability of the innovating sector is larger. since there's larger productivity, larger profitability, people invest more in R&D. With higher spending on R&D, growth rate is faster. So the question from a theoretical point of view, of course, how to sterilize the scale effect, because we want our models to be consistent with the data, right? So in the broad patterns, we want some sort of consistency. So one solution is the semi-endogenous growth. In a couple of papers published by these authors, Jones himself in another 1995 paper. So what they do is introducing decreasing returns in knowledge. Okay, so this phi parameter. So let me introduce this technology. So this is an R&D production function. Okay, so there is this delta parameter which is fixed. LAT is scientists and engineers, let's say, right? So these are the people you employ for developing new knowledge. The new knowledge or new technology is this A dot, okay? And when you employ these scientists and engineers, they of course use the existing state of knowledge or technology as well. So they read papers, they do lab experiments, all this stuff. So they use the existing state of knowledge, but in such models, in these semi-endogenous models, there is this decreasing returns with respect to knowledge. Okay, so this phi parameter is between 0 and 1. So once you do that, once you introduce that type of specification change into the model, then at the end, of course, in a balanced growth path, the long-run growth rate is now limited with population growth rate. So it doesn't depend on population itself. Okay, it doesn't depend on LAT, it doesn't depend on LT. So these are scale variables, but it does depend on population growth rate. Okay, and in a sense, long-run growth rate of GDP per capita is limited by long-run growth rate of population. Okay, so this obviously sterilizes the scale effect, right? Because now if we take the derivative, it only depends on population growth rate. But we don't like this result from a policy perspective. Why? Because in the first generation explanatory models, we kind of proved that policy matters, right? So if government intervenes with the research sector, if the government gives research subsidies, if the government gives perhaps some further incentives for the innovative firms, then the government can affect the long-run growth rate of the economy. But in this model, since demography cannot be easily affected by policies, we have a large literature on that because there are other sociological, economic, and demographic factors. So it is not very easy to change the long-run population growth rate in the economies. So that creates semi-endogenous growth, right? So it is endogenous, yes. It is solved as a function of two parameters, and if you slightly extend the model, you may introduce other parameters as well. But the end result is that policy cannot easily affect growth rate. So the main problem is again this. So the growth rate is independent of how much you spend on R&D, how many people you employ in R&D. Okay, so R&D subsidies and research policy more generally do not change the long-run growth rate. Now the second solution is the set of models where we sterilize a scale effect without changing the policy perspective. Okay, so in these models developed by Pareto, Paul Austin Thompson, Young, and Howitt in the late 90s, they sterilize the scale effect through two types of innovations. Okay, so there is now vertical innovations and there is horizontal innovations. So basically, they merge the two mechanisms, right? In Romer 1990, the mechanism was horizontal innovation. There were new introductions of intermediate inputs as machines. And in the Aghion-Howitt version, it was the introduction of better machines, right? Vertical innovation. Now, in these second generation models, the theorists basically merged the two mechanisms. And importantly, they started modeling innovation at the firm level or the sector level. Okay, because in the first generation models it was the aggregate level, right? So there's only one innovating sector, or if there's there are multiple sectors, they behave as if there's just one sector. And now I'm gonna show you how that actually sterilizes scale effect. But before that, there is a nice remark here by Lenz and Pareto. So the problem is not specification. Okay, so the scale effect problem is not about specification. So there's no reason we should believe that there's decreasing returns to knowledge. Okay, but the problem is measurement, right? So if you measure the entire number of scientists and engineers in the economy, yes, of course it is increasing. But in the meantime, they are diffused over many innovating firms, right? Many different firms, many different sectors that are innovating. So in that sense, there is no scale effect at the firm level. Okay, let me show you how. So that's a very simple model, and we are not going to discuss the full solution, full general equilibrium solution of it, but just to understand the mechanism of second generation models. So here there is this final good. Okay. Now this final good is produced by the services of the intermediate inputs. So these are different intermediate inputs. Okay. So you may imagine that different firms measured by FT. Okay. Let me zoom in a little bit. So there are firms in this economy, and each firm I produces a good, okay, by using labor, and each firm has this productivity level. Okay. Theta is a parameter that determines the substitutability of these different intermediate goods, obviously, right? Now, innovation here is at the firm level, as you see. So each firm has this productivity, and that productivity is subject to change through R&D. Okay, and that's the R&D technology. So as you see, R&D technology has constant returns with respect to knowledge, right? So if you double the knowledge, you double the productivity. Okay, and one simplification here, which makes sense a lot, is that the firm level productivity change responds to all the the average firm level productivities. Okay, why? Because one of the firms just doesn't use its own state of knowledge to produce new knowledge. There are other firms that might create knowledge that is beneficial for this particular firm. All right, so there's this type of externality in the model, and for that externality to work smoothly, we take the average productivities. Okay, so in the economy at time t, there is this average productivity across firms. So if the average goes larger, that's good for everybody. All right, and each firm employs R&D workforce as well. So the total workforce is employed in two different sectors, two different tasks. One task is knowledge production, another task is the good production. And there are F firms in the economy, okay? There are FT firms in the economy, and this is the total labor constraint. Okay, so the entire labor supply is LT, and that's we suppose that it grows, right? So that's typical as well. Now the question is, of course, what happens to FT, right? So if this is vertical innovation, so this one, let me annotate this. Okay, so this one is, of course, vertical innovation, right? So this is vertical innovation, and we have to understand the horizontal innovation as well. Okay, so that's what we are going to do in the next slide. Okay, now we imagine a very simple symmetric equilibrium of this economy. So in the symmetric equilibrium, this is a simplification, of course, but you may not really. I mean, if you want to study a more realistic characterization, you don't have to assume symmetry. But typically, what we do, because our purpose here is to derive the macro results. So if you assume symmetry, we have averages equal to individual levels, right? Each and every firm employ the same level of worker at production, and each and every firm employ the same level of worker in R&D. Okay, so then if you put these results back into the production function, this is what you get, right, at the firm level output. So if you put it inside and do the math, so integral basically vanishes out. So these terms go out, and you take the integral, and you realize total output in the economy now has two components, as you see here. Okay, one is the the technology component. Okay, this part FT theta times AT. So that's the technology component. And remember our let me draw it. Remember our understanding of technology, right, as two-dimensional process. Remember this? So there is this existing distribution, and there is new firms. So these are FT dot, right? And then there is also AIT dot. Okay, so now the total output has this term. Okay, and that's the technology part, and that's basically intangible. And that's tangible. Okay, so these are different types of inputs, and technology progresses when you have an increase in F and then increasing A. So you can actually write this. So if you want to define per worker GDP, you have FT theta, AT, and LYT, LT, right? So obviously, this must go to a constant. And if these two things are growing, then we have growth in GDP per capita, right? So, then what we assume here is this. So we assume that a fraction S of total workforce is employed in knowledge. Okay, so this is the entire flow of workers employed in R&D, right? And that is a constant fraction of total labor force. This, of course, in a fully fledged general equilibrium model, S is endogenous, right? So S depends on the firm's choices. But now we are not solving that because we are interested in demonstrating the result. And that implies, of course, the rest of the workforce is employed for production. Okay, that's simple as that. So what do we get at the end? At the end, we will get this. Okay, so GDP per capita or GDP per worker is this. If you do the math, you realize you have this, okay, because 1 minus S, there's this FT term, right, because LYT divided by LT is at the firm level. So at the aggregate level, you have this parameter now, and 1 minus S will be constant, or, I mean, it doesn't grow anyhow, right? So if you look at the growth rate of GDP per capita will be a function of growth rate of firms, okay, growth rate in the number of firms, and the growth rate of average productivity. Finally, now we can discuss horizontal innovation or product innovation, okay? And that's the simplest way you may imagine, okay? We imagine that if more people are around, then more firms will be established, okay? Because each and everybody has this, let's say, entrepreneurship abilities, okay? There are some opportunities for these entrepreneurs, so they create new firms. There's that flow of new firms, and if that process converges to a meaningful stable equilibrium, then you may imagine, as I will show you in the next hour, you would imagine that the number of firms relative to population is actually constant. Okay, then what you get is this. Okay, now that's the end result. Because remember, we want to find okay, where is my annotation stuff? Oops. Okay. So now you realize the long run growth rate, which is actually a constant, okay, is a function of population growth rate. That's okay, but it is also a function of S, okay? And remember what S is. S is the fraction of people employed in R&D, okay? So if you choose this endogenously, okay, if that S is actually depending on certain fundamentals, then it can be, again, policy relevant. Okay? So in the second generation Schumpeterian models, even if long-run growth rate might depend on population growth rate, it is also depend on what you can change through policies. And look at what ETA is. ETA is also about innovation, right? It's about horizontal innovation. So that's the main result of Lenz and Pareto, but they also provide some empirical basis, okay, some empirical results So let me clear all this to move on. So they study things like this. So what is the long run empirical relationship between real GDP per capita and population growth? There is of course a very weak relationship. So countries with larger population growth rates do not actually have larger long run growth rates, but countries that spend a lot on R&D actually have slightly larger long run growth rates. Okay, so there is some supporting evidence for second generation Schumpeterian models. You may also find interesting papers in the literature. So again, as I said, policy is established through that channel, because now, so let me finish this set of slides. So this paper is very interesting. It's very recent. I think it's published in American Economic Review. So these authors, Charles Jones himself is one of the authors. They revisit this idea of second generation Schumpeterian models, and they really show some evidence on decreasing returns. But it's a kind of strange argument. If you read the paper exactly after the class, if you read it, so you will see what I mean. So in the paper, the main set of findings, so there's a large set of findings, but the main findings depend on a knowledge production function that is not subject to decreasing returns. So Jones kind of retreats. Okay, so he kind of appreciates the logic of the second generation models, because there are some other papers that also find empirical support. Especially there's this nice economist, Jacob Madsen, in Monash University in Australia. So Madsen's papers are also very convincing about reality being consistent with the second generation models. In the upcoming weeks, we're going to go back to this discussion, and we're going to study a particular Schumpeterian model. Now, what I want to do in the next hour is to show you a simple logic of a second generation Schumpeterian model with a slightly more complex stuff, and continuing with our discussion in chapter 4. Okay, chapter 4 of Agüero and Howitt. So let me pause here for your questions and comments, if any. As I said, in the next hour, we're going to look at a particular model of vertical and horizontal innovation, and I will show you several interesting stuff about the policy.
Maybe I skipped. There is a parameter theta. Theta is endogenous, or I couldn't understand.
Theta. Okay, theta is, let me go back to that slide. I think I was a bit fast on that part. So that's the model, right? So that's the fundamental. So theta here is a parameter that basically determines the elasticity of substitution between different outputs, right? So for the production of final goods, you take this composite, you take this composition of different intermediate goods. Okay. So theta is a parameter that is larger than 1, but how large we don't know. Okay, so the elasticity of substitution is equal to 1/1 minus theta, right? So if you do the math here, the elasticity of substitution between any two firm level output outputs is 1/1 minus theta, and we typically assume that theta is greater than 1 in such models. Okay, but we don't know how large theta is. Length and Pareto actually shows this relationship is weak, so they actually show theta must be close to 1. Okay, so if you look at the Length and Pareto paper, this they find this derivative pretty weak. So so if I show you, so now we have this, right? So we have GYT theta minus 1 times n plus what?
Share the...
Oh, sorry. Okay. So it is like delta S 1/eta, right? Now S is again Ft times LAT divided by LT, right? So Length and Pareto show us that in the data, this relationship is close to 0. Okay, so what does it mean in theory? In theory, it means theta is close to 1. Okay, because that part is weak. Instead, if you look at the R&D shares at the firm level, okay, S, so you find that in the data as well. Okay, so the elasticity of substitution is 1/1 minus theta, and if theta is close to 1, right, what happens? That increases, right, until infinity, right? So it kind of, so the data kind of suggests, if you impose this model to the data, it suggests elasticity of substitution is rather large, right? So if theta is close to 1, the production function is close to a linear function. So you learn something about the the aggregation principles by looking at the macro implications of the model. I'm not sure whether that was clarifying enough.
Thank you. The last question. So the second generation models are fully endogenous, or?
Yes. I mean, they are fully endogenous. If you forget about that population growth part, they're endogenous through this. So in a full model, Salman, in a full model, S and eta are endogenous. Okay.
Yes.
Because there is a we will discuss this in a couple of weeks later. So in a model like this, establishing a firm is kind of owning an asset, right? Because that's a firm. So there is a return. So all of this is asset pricing, my friends. Okay. So it's a general equilibrium framework. People save, they obtain some returns, right? So they save money, so there is a return in the market. So they can put their money into a bank account, right, to obtain some interest income, or they can buy some stock shares of firms. So establishing new firms create new value in the stock market, right? Or they can also invest in knowledge, right? Knowledge is a stock variable. It has a return as well. So both types of innovation has a return. Okay, one is, I mean, both of them have real return, and in equilibrium, with no arbitrage, of course, those returns will be equal. All right. So people will be indifferent. People will be indifferent between three options. Put your money into a bank account, okay, for interest income. Invest your money in stock shares of firms, or invest your money in R&D firms, startups. Okay. So it is all asset pricing. So once these decisions are taken optimally, this S parameter and eta parameter, they will actually be endogenous. Okay, so policy again can affect people's choices through subsidies, taxes, and other stuff, right? So that's the notion. In second generation theory models, we can put back policy in.
Okay, thank you.
I will show you in the next hour. Okay, so then if you have no further questions, let's take a break. And after the break, I will give you a simple model in this tradition, and discuss some implications for policy. Okay. So it is now 10:20. Let's meet at 10:35. Is that okay for everyone?
Okay.
All right. Let's meet at 10:35 and continue.
Thank you.